Welcome to the Deep Dive. This is where we take source material you're interested in and, well, we help you get up to speed fast.
That's right. Think of us as your research buddies. You're the learner, you want those aha moments, but, without drowning in information.
And today, one of you pointed us towards a really fascinating study. It looks at how computer science students and math students learn introductory programming.
Yeah, the listener was interested in, the different ways people learn this stuff and maybe how we can make learning better for everyone.
So for this deep dive, we've got two main sources. There's a science news piece from yesterday, pretty accessible overview.
Right, mapping learning paths and intro programming. CS versus math. Good summary.
And then we've got the full academic paper itself.
Yeah, Tracing Distinct Learning Trajectories is a long title. Sequence analysis of score, engagement, and code metrics for CS versus math students from the International Journal of STEM Education.
Published just this month, May 2025, by Gao, Yan, Liu, and their colleagues.
And the key thing, like you mentioned, is this sequence analysis approach they used.
Yeah, that really jumped out at me. It's not just about the final exam grade. They mapped out the whole learning process week by week. It's something you see more in, social sciences, right?
Exactly, because intro programming, it's so foundational, but students come in with such different backgrounds, different ways of thinking.
Makes it tough to teach, I imagine.
Totally. How do you design a course that works for everyone? And, just looking at the final grade often misses how students actually got there, the struggles, the breakthroughs.
Okay, so let's dig into that method. How do they track these learning paths using sequence analysis?
Well, instead of just the final score, they looked at things over time. They tracked performance on weekly tests. There were 12 of them, plus the final exam.
Okay, the scores. What else?
Engagement. So how often were students submitting code attempts? How much time were they actually spending on the online system where they did their work?
Right, the active engagement part.
And then, and this is really cool, they analyzed the code itself.
What do you mean, like how good the code was?
Sort of. They looked at metrics like code length, its complexity, the kinds of structures they used, basically trying to quantify the, let's say, style and sophistication of their programming over time.
Interesting. So tracking not just if they solved it, and how.
Precisely. The goal was to see if the CS and the math students approached problem solving differently in their code and how that changed throughout the semester.
And who are the students in this study?
They had 75 students, all novices, meaning no prior programming experience. 35 were math majors, 40 were CS majors.
And crucially, they were all in the same class.
Yep, a compulsory Intro-C programming course.
Yeah.
Same instructor, same assignments, same lectures, mixed class.
So they tried to make it a level playing field from the start.
Yeah.
What did the course actually cover over this 16 weeks?
It was pretty standard for an intro course. Started with basics like variables, expressions, then moved into conditionals, loops.
The building.
Exactly. Then arrays, strings, functions, pointers, structures, the core concepts you need in C.
And each week had a test.
Yeah, an online test each week for formative assessment, checking understanding along the way. And then the big final exam, the summative assessment.
You mentioned it was a mixed class. Did they do anything to make sure the difficulty was fair for both math and CS students?
They did. The paper mentions that both the CS and math departments actually reviewed and adjusted the course content and difficulty.
Okay, so it wasn't just skewed towards one group.
Right. And the instructor used face-to-face teaching, plus this online judge system for submitting and checking code. Treated everyone the same.
Okay, so they gathered all this data scores, engagement clicks and time, code complexity. How did they put it all together?
This is where the sophisticated analysis comes in. They use something called latent class analysis, LCA, to find natural groups based on engagement patterns.
Okay.
And for the code styles, they used self-organizing maps, SOMs, which helps cluster similar coding approaches. Then, sequence mining techniques help them see how students moved between these different states, different levels of engagement, code style, and scores over the 16 weeks.
Wow, that's definitely going beyond just looking at the final grade. Like the Science News article said, it's very process-oriented.
Exactly. Most older studies just looked at outcomes, pass-fail, grade A or C. This gives a much richer picture of the actual learning process.
All right, the moment of truth. They did all this complex analysis.
Yeah.
What did they find? How did the learning journeys of CS and math students actually differ?
Well, there were some pretty significant differences, especially in how engagement related to scores.
Okay.
For the CS students, it was more, let's say, predictable. High engagement, submitting often, spending more time generally meant higher scores. Low engagement, lower scores.
Makes sense. Put in the work, get the results. What about the math students?
That's where it got interesting. For them, yes, low engagement usually led to low scores, no surprise there, but high engagement didn't always lead to high scores, especially later on.
Hmm. So putting in the time wasn't a guarantee of success for them.
It seems not, or at least the relationship was more complex. It suggests maybe they were engaging differently or perhaps less efficiently.
What else? You mentioned code complexity.
Yeah, they looked at students who wrote particularly complex code. They called it over-engineering. The CS and math students actually showed opposite trends in this over the
It's
semester.
opposite trends. How so?
The paper goes into detail, but essentially how this tendency changed over time was different between the two groups. And another key thing, formative versus summative scores.
The weekly tests versus the final exam.
Right. For CS students, their weekly scores were a pretty good indicator of their final exam performance, suggested the tests were reflecting their actual understanding.
Okay. But not for the math students.
Not always. They saw what they termed cold start and learning avoidance phenomena, particularly among the math major.
Cold start and learning avoidance. Okay, let's unpack those. What does cold start mean here? You know that feeling when you start something new and just feel stuck?
Exactly like that. The math students were more likely to start the course off with low engagement, low scores on those code metrics, and low test scores.
A rough start.
Yeah, and what's crucial is that they found it harder to pull themselves out of that state, even though it was a required course, even with weekly tests.
The motivation wasn't kicking in early.
It seems that way for some. Maybe less initial confidence, or maybe struggling to connect programming to their, mathematical way of thinking immediately.
Okay, so a tougher beginning. What about learning avoidance? That sounds deliberate.
It's a really interesting finding. They found about 20% of the math students did pretty well on the weekly tests,
Okay.
but then had a big drop on the final exam.
Oh, why?
The researchers speculate that maybe these students were focused on just sort of getting through the weekly hurdles, maybe finding answers online, getting help, focusing on surface-level task completion.
Without really getting the core concepts.
That's the idea. So those weekly scores didn't actually reflect deep understanding, unlike for the CS students where they mostly did. It's like they were acing the quizzes but hadn't truly learned the material.
That's a huge difference. Good grades masking a lack of real learning. But you said engagement did pick up for math students later.
Yes, interestingly, the link between engagement and final scores got stronger for math students later in the semester, especially around the midterm.
Ah, so maybe the pressure of bigger exams motivated them more.
That seems plausible. Exam pressure might have spurred more focused effort for some.
Okay, that paints a clearer, if somewhat complex, picture for the math students. What about the CS students' trajectories?
Well, generally, they were more likely to hit a high performance level and just stay there. More consistency throughout the course.
Okay.
And here's a fascinating twist. Later in the semester, some CS students actually showed less engagement or wrote less complex code.
But their scores didn't drop.
Right. Sometimes their scores even improved.
So they got lazy.
Not necessarily. The researchers think it might show they were becoming more efficient. They'd figured out how to solve problems effectively without needing as much time or, overly complicated code.
Ah, like they learned how to learn programming, became more strategic.
Exactly. Better metacognitive skills for this specific domain. They could get the same or better results with less apparent effort.
These different paths are really telling. How did the researchers tie this into the idea of computational thinking?
They suggested that these changing links between effort, code style, and scores really reflect how students were developing computational thinking.
Which takes time and effort initially.
Right. At the start, you have to put in a lot of work just to build those mental models.
Yeah.
But once you get it, you become more efficient.
So the math students with high engagement, but maybe lower scores or complex code, might still be grappling with developing that core computational thinking efficiency.
That's one interpretation, yeah. Still working hard, but maybe not yet thinking like an experienced programmer.
It's like building a new kind of mental muscle.
Yeah.
They also mentioned something called goal congruity theory.
Yeah, goal congruity. The basic idea is that we get more invested in things if we see how they align with our personal goals and, our identity.
Okay.
So Even though math is super relevant to CS, the math students might not see programming as, central to being a mathematician in the way CS students see it as core to being a computer scientist.
So even if they have the aptitude, the personal relevance or motivation might be different, affecting how they engage, especially early on.
That's the hypothesis. It's not just about skill, but about how you see this fitting into your future.
That makes a lot of sense.
Okay.
Bringing this down to earth, what are the practical implications? What should instructors take away from this?
Well, first big thing. Don't just look at the class average. It hides these really different journeys.
Right, you need to see the individuals?
Exactly. Instructors need to be aware of these potential patterns at different stages, pay attention to different groups.
Like who specifically?
They suggest keeping an eye on those low engagement, low score students right at the start. Try to intervene early to avoid that cold start becoming permanent.
Makes sense. Catch them before they fall too far behind.
And later on, maybe look at students with really high engagement but overly complex code. They might need help with efficiency. And definitely be aware of that potential learning avoidance among non-majors who seem to be doing okay on weekly stuff.
So look beyond the surface scores for some students.
Precisely. Encourage deeper understanding, not just task completion.
Any suggestions on course structure or assessment?
They float the idea of maybe increasing the weight, or at least the frequency, of those early formative assessments.
To encourage that early engagement.
Yeah, try to combat the cold start issue, get everyone locked in sooner. They also briefly mused about university structures. Maybe having an undecided major option could help students find the right fit before committing.
Interesting thought. Give them space to explore. So lots of good food for thought for educators there. If we were to sum up the absolute key takeaways for you, our listener.
I'd say the main message is that learning programming isn't one size fits all, especially when you have students from different backgrounds like math and CS.
Their paths can look really different.
Totally. This study shows clear distinctions in engagement patterns, coding styles, and how well early scores predict final understanding. Math students might face unique hurdles like cold start or learning avoidance.
While CS students might stabilize performance sooner and potentially become more efficient learners over time.
Right, and it underlines the value of looking at the process of learning, not just the final grade.
And the implications go beyond just CS and math, right?
Right.
It speaks to how diverse learners tackle any new complex subject.
Absolutely. Understanding these journeys helps us think about more inclusive, more effective teaching everywhere.
So here's a final thought for you to chew on. Think about your own learning. When you've tackled something really challenging, did you notice yourself or others taking different approaches?
Yeah, how did your effort, your engagement, connect with how deeply you actually understood it? Was just doing the assignments enough?
And zooming out, what does this study make you wonder about how we teach and learn other subjects? Not just coding, but maybe languages or sciences or anything complex. Are we paying enough attention to the process?
Definitely something to think about. And if you want all the fine-grained details, the original paper by Gao and colleagues is out there. Lots more depth on their methods and findings.